Hello and welcome. In the last video, we talked about how the first derivative actually tells us a lot about the graph of a function. How if the first derivative is positive, then the function is increasing because the slope, which is the derivative, is positive. We talked about how if the first derivative is negative, the slope or a graph is decreasing, and how if we are changing sign from positive to negative or from negative to positive, which would cause the derivative to be zero, that we actually have a relative extrema, a relative maximum or a relative minimum at that particular value. What we're going to do in this lesson is extend that idea further. If the first derivative tells us where a function is increasing and decreasing, what does the second derivative tell us? That's going to be the focus of this lesson. The second derivative actually tells us about the concavity of a graph. And the concavity is sort of the curvature, the way that it's opening, and the shape that that makes. So a graph that opens upward, or that is cup-shaped, it's U-shaped, is said to be concave up. And concave up, so you can see this curve here, it is opening upwards, it is looking like a cup. And the tangent lines, if I were to draw a tangent line, every tangent line I draw would actually be below the graph, otherwise it would intersect the graph more than once, and then it wouldn't be a tangent line anymore. And what is happening is, as I create more tangent lines going around this curve, the slopes are getting less and less and less steep, and they're changing as they curve around the curvature, basically, as they go around the concavity of a graph. And what that means is that the tangent lines are increasing, or the second derivative is positive. So any graph that is concave up, that means that in that portion of the graph, the second derivative is positive. So again, what we just pointed out is that anywhere that a function or the graph of a function is concave upward, and you can see that U shape, the second derivative is positive in that particular area. Now, similarly, if we start talking about the opposite of that, so if we start talking about concave down, meaning it sort of is hill-shaped or frown-shaped, it looks like an upside-down U, we would say that that is concave downward. So similarly to what we just said above, anywhere a function or the graph of a function is concave downward, if you were to look at the value of the second derivative there, that second derivative would be negative on that interval. So again, the first derivative helps us identify where the function is increasing and decreasing and where that is changing, relative extrema. The second derivative helps us identify where a function is concave upward, opening up and U-shaped, like a smiley face, or concave downward, the second derivative would be negative and it would make sort of a frowny face. So what I actually want you to do is to take a look at these two graphs in A and B and try and trace the part that looks like it's opening downward, concave downward, and then the same thing for the parts that are concave upward, and then unpause the video and see how you did. So hopefully you had some time to kind of look at these graphs and see how the concavity is behaving. Let's go ahead and write as intervals what this looks like. So for A, it looks like the graph is concave downward, which I'm going to use CC down arrow. It looks like it's concave downward from negative infinity, if we suppose that there were arrows on the ends of these graphs, from negative infinity until it gets to 0. And then at 0, it looks like it stops behaving in that way, and it starts changing to be concave upward on the interval from 0 to infinity. On B, it looks like it is concave downward at both ends, which makes sense. This looks like it's a quartic function or something to the fourth power. And I can't tell exactly where it changes, but let's say it changes around x equals -1 and +1. Again, we can't tell exactly from this graph, but we can say that it's concave downward from negative infinity to maybe -1, and from, let's make this fit a little better, and from +1 to infinity. which would mean that it's concave upward. It's U-shaped, opening upward just between those two values. So the other thing I want to point out is that something must be happening. Just like where our functions change from increasing to decreasing, we can identify that we have relative extrema. Something must be happening when we're changing from concave downward to concave upward. That point must have some sort of significance. And that's what we're going to talk about next. What is that point called? How do we find it? And how do we use it? So these points where the graph is changing concavity are called inflection points. So at some point, a graph can change from concave upward to downward or vice versa. These points are called inflection points. The way that we identify them from a graph is just trying to see that point where it's starting to change concavity. And we're going to talk about how to find it from an equation or from the function itself as well. But some key things we need to know about these inflection points are that, first of all, in order to have an inflection point at a particular value, the tangent line has to exist at that particular value, meaning the first derivative has to exist. The second thing that we need to know is that the graph has to actually change concavity, which would mean that the second derivative is 0 or undefined, and the second derivative is changing sign, right? If the second derivative was negative and negative, then we're not changing. That whole section would be concave downward. So what you're going to see in just a minute is that the mathematical approach that we take to find points of concavity is going to look a lot like what we did when we were finding relative extrema. But let's look at this graph and answer these questions first. So use the graph to the right to answer the questions that follow. On which intervals is the graph concave upward? So let's see if we can identify where it's concave upward. Well, it's definitely concave upward here. It looks like it's concave upward here. It's sort of hard to tell, but this little piece between 3 and 4 sort of looks like a straight line, and a line doesn't have concavity, so we're going to maybe come back to that piece. This piece definitely looks concave upward. So let's go ahead and identify those intervals. So it looks like we are concave downward from -2 to -1. From +1 to +3, and from 4 to 5. It looks like we're concave downward here and here, so that would be -1 to +1 and 5 to 6. And then on what intervals does the graph have no concavity? And that looks like here, again, because this piece is linear, so the first derivative would be a constant, and the second derivative would be 0, which means that the second derivative isn't positive or negative, which means it just doesn't have any concavity. And then there's sort of a sneaky little piece right here that does have points and is a part of our function. So there's no concavity between 3 and 4, and there's no concavity between 6 and 7, because the slope, the second derivative would be 0, or because those are sort of linear looking pieces which don't have concavity. So inflection points are where we are changing concavity. So it looks like we have an inflection point here. It looks like we have an inflection point here. And here we're changing from concave up to no concavity. That's not going to be an inflection point because, again, the second derivative wouldn't be changing sign there. It would be going from concave up, so from positive to nothing. So this would be our other point. So we have points, inflection points, at -1, 1, at 1, 1, and at 5, 1. This isn't always the easiest thing to be able to tell from a graph. This graph was pretty zoomed in and pretty easy to tell where things were changing, but it's much easier to be able to mathematically verify for ourselves where a function is changing concavity. So what we're going to do is we're actually going to find the first derivative, use that to find the second derivative, figure out where our second derivative is equal to 0, and make a number line with our second derivative. and then determine where the second derivative is changing signs. So this is a lot like the first derivative test that we used to find relative extrema. So let's walk through this together. The very first thing that we're going to do is find the first derivative and the second derivative. So go ahead and pause the video and find the first derivative and the second derivative. So here we have our first and second derivatives. Both of these exist everywhere since they're polynomials. So in order to find our possible points of inflection, which I'm going to abbreviate as PIP, possible inflection points, we want to know where our second derivative is either undefined or 0. And in this case, since it's defined everywhere, the only thing that we're going to look for is where this is 0. So I'm going to go ahead and factor out the greatest common factor here, which is 6, to make this a little easier to solve. And now I can factor this and divide the 6 out. So this is going to be 2x minus 1 times x plus 1. So my x values are going to be 1/2 and -1. The next thing we're going to do is we're going to make a sign chart or a number line with the values that we just found for our second derivative, just like we did for the first derivative. So I'm going to come over here. I'm going to put -1 and positive 1/2 on my sign chart. I'm going to be looking at the second derivative and asking myself, when we are below -1, what's happening? Well, if I'm below -1, say at -2, this is going to be 48 minus 12 minus 6, so that's going to be positive, whatever that number is. If I plug in 0, I get -6, so that's going to be negative. If I plug in something bigger than 1/2, like 1, I'm going to get 12 plus 6 minus 6, that's also going to be positive. So now we can use this sign chart to write our intervals of concavity. Right? Anywhere that the second derivative is positive, that means that our function is concave upward. So f is concave upward from negative infinity to -1, and from 1/2 to infinity, since f double prime of x is greater than 0. And f is concave downward from -1 to positive 1/2, since f double prime of x is less than 0. Let's give ourselves a little bit more space here. There we go, that's better. So the only other thing we need now are to identify what our inflection points are. So that's going to be our step 5, find our inflection points. Our inflection points occur at any x value where the second derivative is changing its sign. It doesn't matter if it's changing from positive to negative or from negative to positive. We're not identifying relative extrema. All that matters is that it is in fact changing sign. And that's happening at both of our x values. So we have inflection points at x equals -1 and at positive 1/2, since f double prime is changing sign. And if we wanted to find the exact coordinates of those points, we just found our x values, we would plug those back into the original function to find the y values. But for time's sake, I want to point out that that's how you would do that, but I would rather spend our time looking at a couple more examples. So let's move on and look at a couple more examples. All right, so let's go ahead and do number 6 together. But I'm going to, again, encourage you to kind of do each piece on your own. So first, find both the first and the second derivative, and then go ahead and figure out where the second derivative is equal to 0 or undefined, and then unpause the video and see how you did. So here we have our first and second derivative, and if we set our second derivative equal to 0, we're going to get one inflection point, and that's going to be at x equals 1/2. If I set this equal to 0, I would subtract 1 and divide by -2, which would give me positive 1/2. Note that all three of these functions are polynomial, the original, the first derivative, and the second derivative, so they are defined everywhere. So the first derivative exists everywhere, the second derivative exists everywhere, the function exists everywhere. So we found our inflection point, and now we found our possible inflection point. Now we need to make a sign chart to see if our second derivative is actually changing sign here. So 1/2 is going to be here. If I plug in something below that, like 0. If I plug 0 into my second derivative, I'm going to get positive 12, so that would be positive. If I plug something like positive 1 in, I'm going to get 12 minus something that's bigger than 12, so that's going to be negative. So we can now identify our intervals of concavity. We're concave up, where the second derivative is positive, so we're from negative infinity to positive 1/2, we are concave up, since g double prime of x is greater than 0. And from 1/2 to positive infinity, we are concave down, since g double prime of x is less than 0. Which also means that at 1/2, we are changing from positive to negative. So we have an inflection point when x equals 1/2, since g double prime of x is changing sign. All right, I encourage you to pause the video and see if you can work through number 7 completely on your own. Notice that we're on a closed interval from 0 to 2 pi. So go ahead and pause the video and work through this on your own. So here I have my first and second derivative. I set my second derivative equal to 0. Again, sine and cosine are defined everywhere, so we don't have to worry about where our first or second derivative is undefined. So if I have sine of x equals negative cosine of x, I'm basically asking when are sine and cosine opposite in signs, right? So here they're both positive. Here we have cosine is negative and sine is positive. Here they're both negative. Here, cosine is positive and sine is negative. So they're opposite in sign in these two quadrants, which would be quadrant 2 and quadrant 4. And they are the same when we are at pi over 4 intervals. So in this quadrant over here, this would be 3 pi over 4. And in the bottom right, or in the fourth quadrant, that would be 7 pi over 4. So these are my possible inflection points. So go ahead and make your sign chart and work through the rest of this problem and then unpause the video and see how you did. Okay, so here is my sign chart. I'm asking myself something between 0 and 3 pi over 4. So let's just say in my head I'm thinking pi over 2, and let's see if our second derivative is positive or negative. If I plug in pi over 2, negative cosine of pi over 2, well, that whole thing is just going to be 0. Cosine of pi over 2 is 0. Sine of pi over 2 is 1, and then it's going to be negative. So this is going to be a negative area. If I plug in something between 3 pi over 4 and 7 pi over 4, let's say pi. Cosine of pi is negative 1, so I have the opposite of negative 1. Sine of pi is 0, so this is going to be a positive section. And then last but not least, if I'm looking at the region between 7 pi over 4 and 2 pi, I could think about the point that is at 11 pi over 6. And that point would be root 3 over 2 negative 1/2. So the cosine value is bigger. So I would have negative root 3 over 2 minus the sine value. So this is going to be a negative number because root 3 over 2 is bigger than 1/2. This is going to be a negative number. So now go ahead and pause the video and write your intervals of concavity and identify the x values of your inflection points, and then unpause the video and see how you did. So here we go. You can check over those intervals. Make sure you're justifying. You're saying why you know those are happening. And when you're done checking over those, you can unpause the video, and we're going to move on to our last new topic for this video. So what the majority of this video has been about was how to use the second derivative to talk about the concavity of a function. The cool thing is there's another application of the second derivative. We can actually use the second derivative to help us identify relative extrema. And you may be thinking, isn't that what the first derivative is for? And that's true, and that's still a part of this. But what we can actually figure out is that if we had a point that we knew was possibly a relative extrema, if we knew that the graph was concave upward there, we would be able to say that this is a relative min, because if the graph is concave up and we knew that this was possibly a relative extrema, then it would have to be a minimum. Similarly, if we had a point that we thought was a relative extrema, meaning the first derivative was 0 or undefined, and we knew that it was concave downward there, we could say that this is a relative maximum, because if it's concave downward and the first derivative is 0, that would mean that we would have a relative maximum there. So a couple things that I want to point out as we're working through this. First of all, is that this test is called the second derivative test for relative extrema. This test does not require you to make a number line, and it does not find points of inflection. So we just spent a bunch of time finding inflection points. That is not what we are using this test for. We are using this test to find relative extrema. And here's how this test is going to work. The first thing you're going to do is find the first derivative and find the critical numbers. Then, instead of putting the critical numbers on a number line, you're actually just going to find the second derivative and plug those critical numbers into the second derivative to determine the sign. So we're using this to figure out the sign, and by sign I mean plus or minus. If the second derivative is positive, then we would have concave up. That means that we would have a relative minimum. If the second derivative is negative, that would mean the graph is concave down and we would have a relative maximum. If the second derivative is 0, then we don't know anything, and you would have to use some other test to get there. So remember, we only know something, or we can only use this test if the second derivative is positive or negative. If the second derivative happens to be 0, then we're going to have to use something else to determine our relative extrema. So let's look at an example. Use the second derivative test to find the relative extrema. So go ahead and pause the video and find your first and second derivative and find your critical numbers. So here I have my first and second derivative. I'm going to set my first derivative equal to 0 to find my critical numbers. So I'm going to factor negative 12x out, which leaves me with x squared minus 1, which means my critical numbers are 0 and plus or minus 1. So what the second derivative test says is that you can take the second derivative and plug those critical numbers into the second derivative. If what you get when you plug them in is positive, that tells you that the graph will be concave upward and you would have a minimum there. If the second derivative is negative, that would tell you the graph is concave downward there and you would have a maximum. So if I plug 0 into my second derivative, I get 12, which is positive, which means concave upward. That means that we have a relative min at x equals 0, since f prime of 0 equals 0, and so both of these things have to be true. The first derivative has to be 0, and the second derivative at 0 is positive. So that's why we have a relative minimum there. Now, if you look at what happens when we plug in both 1 or negative 1, we're going to square that and multiply it by negative 36 and then add 12. So both of those values of the second derivative are going to be negative, which means they're both going to be concave downward. So we can say that we have a relative max when x equals plus or minus 1, since the first derivative is 0 there and the second derivative is negative. So both of those things have to be true. The first derivative has to be 0 and the second derivative has to have a sign that indicates whether the graph is concave up or concave down. All right, I encourage you to pause the video and try and work through 8 and 9 on your own. I'm going to clear a little bit more space and then unpause the video and see how you did. So here I have the first and second derivative for number 8. I set the first derivative equal to 0 and got two critical numbers, 0 and 2. So I want to know what happens when I plug 0 into my second derivative and what happens when I plug 2 in. And remember, it doesn't matter what number comes out, it just matters the sign. So if I plug in 0, I'm going to get negative 6, but really what matters is that the second derivative is negative. So it's concave downward there, which means that at x equals 0, we have a relative maximum. If I plug in 2, I get 6 times 2 minus 6, which is going to be a positive number, which means we have a concave upward part of the function, which means we have a relative minimum. So we can say we have a relative max at x equals 0 because of two things. The first derivative of x is equal to 0, and the second derivative of x is negative. Similarly, we have a relative minimum at x equals 2, since the first derivative is 0, and the second derivative is positive. So you need to have these justifications here in order to accurately say and prove that what you're saying is true. If you haven't already, go ahead and pause the video and work through number 9, and then unpause the video and see how you did. All right, for number 9, we have our first derivative being negative 2x plus 2. Our second derivative is negative 2, which means this function is concave down everywhere, which means this critical number, which makes our first derivative 0, must be a relative maximum. So we have a relative max at x equals 1. Again, if we wanted to find the coordinates of this point, we could just plug 1 in. If we plug 1 in, we're going to get negative 1 plus 2 plus 1, which would just be 2. So if we needed to actually identify the inflection point as a coordinate, we could do that as well. So how do we know this? We know this since y prime is equal to 0 and y double prime is negative. That's how we know that we have an inflection point there. We're going to do one last example just to push us a little bit. It's more of an abstract example, and then we're going to recap what we covered this video. All right, so here is our challenge problem. It says g of x is a function such that, and then we're given a bunch of information. It says find the x values of the relative max and min when possible. And I'm going to add that we should assume that this function is continuous. And I'm going to I want you to pretend that it said that there, that we have g is a continuous function. So the best thing to do when we're given this much information is to really start by actually just making a table of values. So we're given some x values, we're given the value of the first derivative at some of those x values and the value of the second derivative. So go ahead and pause the video and fill in and create your own table. So hopefully you had enough time to create a table that looks similar to my table. Now that we have this organized and we know that g is continuous, let's see what we can actually tell from this table. So first of all, at x equals 3, at x equals negative 3, the first derivative is 0 and the second derivative is positive, which means that this is concave upward. So we have a relative min, and we can say since g prime of x is 0 and g double prime of x is positive. At x equals negative 1, the first derivative is 0 and the second derivative is negative, so we have a relative maximum since g prime of x is 0 and g double prime of x is less than 0. At x equals 0, we don't know what's happening based on the second derivative test. We can't use the second derivative test here because the second derivative is 0. So we're not really sure what's happening there. There could be an extrema there. We just don't know. We can't conclude anything in this case. Similarly, at x equals 1, we can't conclude anything because we don't know what's happening with the first derivative at x equals 1. So nothing can be concluded there. And then last but not least, at x equals 2, we don't have any extrema, no extrema, because the first derivative isn't even 0 there, since g prime of x is not equal to 0 at that x value. That means that there are no relative extrema at that value, because two things have to be true. The first derivative has to be 0, and the second derivative has to not be 0 in order for us to conclude anything. So let's recap what we covered in this video. The first thing that we talked about in this video is what concavity is and how that ties to the second derivative. So we talked about concave upward being a U-shaped graph, or a U-shaped portion of the graph, and this means that the second derivative would be positive, and how concave downward would be a frown-shaped part of the graph, and how that would be related to the second derivative being negative. We looked at how to identify concavity given a graph of a part of a function, and that led us to talking about how at some point in time, the graph can be changing from concave downward to concave upward, which led us to our second thing that we covered, or our second topic, which was an inflection point. We talked about how an inflection point has to happen when the first derivative exists and the second derivative is either 0 or undefined. We talked about identifying those from a graph, and also how to use a number line or a sign chart and the second derivative to calculate inflection points, looking for changes in sign of the second derivative to identify inflection points, and using that same sign chart to identify intervals of concavity. And then we wrapped up this lesson, lastly, by talking about the second derivative test, which helps us identify if a relative extrema is, or if a critical number is a relative max or min. And we use that by making sure that the first derivative was 0 and looking at the sign of the second derivative. And that enabled us to be able to determine if it was concave up, that it was a minimum, and if it was concave down, that it was a maximum. So go ahead and write down any questions you have and post them below, and I look forward to supporting you on this. Thanks for listening.